let's say P is the pointer. P is the pointer type. And you copy the value of the location of the element of I to pointer P. Let's say you have some C code like this. Then this pointer P will hold a pointer that points to the element X of I, right? Without accessing the memory. It only, but it doesn't really access the memory, right? So this LEA instruction is used for this case. So it computes address, but without accessing the memory location. Okay, so and this also is used for computing arithmetic expression of the form x plus k times y. Because if you want to compute any expression in the form of x plus k times y, you can use LEA instruction. Okay, let's think about these examples. This is the simple function that actually returns take an integer value and multiply it by 12 and returns the value. This very simple function. So in this case, this function can be implemented using this LEA instruction. Let's think about these two instruction. The first of all, LEAQ. So this one is similar to the addressing mode we have seen in move instruction, right? It actually has 3 or 4 different operands, 2 registers and 2 constants as before. So but this one is almost like a move instruction, right? Difference from the move is that it only uses the accessing it. Okay, so it simply just computes the address and computed the value to the register. Okay, that's the difference between this instruction and move. So if you actually had move here, then move instruction will actually access the memory location and copy the value from there, right? That's a move. But in LEA, you only compute the address and copy the address value into the register. So here, let's take a look how this one will be computed. So if you see, if you remember in the previous general addressing mode, this one will be computed something like RDI plus RDI times 2, right? So it will be 3 RDI. And our assumption is that the X is in RDI register. So this, as a result of this computation, this RAX will hold 3X. In the second instruction, we actually shift this value to the left by 2 bits, meaning this one is multiplied by 4, right? So as a result, now this RAX value will actually have a 12X, right? Because the first instruction actually multiplied the X by 3, and second instruction actually multiplied that value by 4. So eventually, we're gonna end up having a 12X value in register RAX. Okay. Okay. Right. Actually, also x86 64 also defines some 2 operand arithmetic. So add Q, sub Q. Again, these Q's are a suffix indicating 64-bit register, 64-bit operands. So if you do a 32-bit computation, it will be L instead of a Q. So add Q, sub Q. Then for example, in add Q, the destination value is set to a sum of the 2 registers, a destin source, right? And sub Q, in this case, it calculates the difference between destin source and store the result back to destination register, destination an operand. Okay, and mul Q, sal Q is a shift to left, shift to left instruction, and SAR, there are 2 different versions of shift to right, arithmetic shift and logical shift, right? So SAR is arithmetic, SHR is a logical. XOR and Q, OR Q, they are all logical, bitwise and bitwise XOR and so on, right? So they, this Intel architecture support various arithmetic and logical operations. Watch out for argument order especially if you do like a sub, they are not commutative, right? So you have to be careful about the argument order. And there's no distinction between signed and unsigned integer, right? We already learned that you can actually use the same hardware for both like a signed and unsigned arithmetic because they are isomorphic, right? So we already covered that thing. So you can actually use so there's no between signed and unsigned integer. So eventually, if you provide the same bit string as input, then the output bit string will be always the same, regardless of whether it's like a signed or unsigned integer, right? So in high hardware level, in ISA level, it doesn't distinguish these two. But as a user of the instruction, you can actually interpret it as like a signed integer or unsigned integer, but you see like your interpretation of the bit string, right? 멀은요, multiply. i는 인테저. fmol도 있어요, fmol. fmol은 이제 floating point. 네, 네. integer multiply. 네. Any other questions? Okay. Also, there are one operand instructions such as inc, dec, neg, not. So they are like increment the value by 1, decrement value by 1, like a negation, like a change the sign of the value, or not. Basically, you take the bitwise not for all the bits in the vector in the register. Please refer to the book for more instructions. So here is like an arithmetic expression example. So let's say you are given a C code like the one shown in the left. Arith function, it takes 3 integer value x, y, and z, and it performs various like intermediate computations in add, multiply, and so on, and finally it returns the value of rvel. Okay. So if you compile this code, the example like output code looks like this. It uses like LEA, add, SAL, all these things. If you remember, LEA is like address computation. It computes some expression and computes like a linear expression and copy the resulting value to the register or some like a destination, right? That's LEA. And SAL is like a shift left, multiply equivalent, multiply by 2 to the power of n, right? Multiply is shift or multiply by 2 to the power of k, right? I mul q is like a multiplication, it's a multiply. But even though that there are 2 multiplies here, it's only used just once, right? Because in this case, we can this like a multiply a constant value can be replaced by shift and LEA. So it actually takes like a less effort to compute than using like a multiplier. So here is the arithmetic. Here's the example. So let's take a look. This code one by one. So here's the assumption. These 3 arguments, x, y, z, are initially placed in register RDI, RSI, and RDX. Okay, these are 3 registers that initially hold these 3 arguments passed by the caller of the function. So here, the first instruction, it actually computes the value of T1, right? Why? Because if you see this, like this, then this expression is nothing but a sum of these 2 registers, right? So RDI plus RSI. So as I said, RDI holds the value of x, RSI holds the value of y. So if you compute, this part, it will be actually x plus y. This x plus y value will be copied to register RAX. So now this RAX register will hold the value of T1. Okay. The second instruction, so we add z to this like a T1 value. Okay, so in this case, because Z is actually being held in register RDX, so if you execute add instruction, it will basically compute the sum of these two. So it will be like a T1 plus Z. So T1 plus Z, or Z plus T1, will be stored in the register RAX. Okay, so now after you execute this instruction, this RAX will hold the value of T2. Right? What about the third instruction? If you see the third instruction is again like LEA, like a load effective address instruction, that it first compute this expression, RSI2. Then eventually this value will be 3 times RSI. Because it's RSI plus RSI times 2. So it will be a 3 RSI. So, but initially this Y actually had this RSI register holds the value of Y. So this part will be actually 3Y. The value of 3Y will be stored in RDX. And in the next instruction, we shift this RDX register to the left by 4 bits. Okay? So shift to left by 4 bits is equivalent to multiply by 16, right? Because we actually 2 to the power 4, right? So it'll be, now we multiply this value by, and multiply by 16, then eventually we're going to get like 48Y. 48Y, and that value will be stored in RDX register. And so in this case, by using these two instructions, we effectively compute a multiply without using multiply instruction. That's the. So there's also like a historic reason. Like old computers, like old CPU, multipliers were really expensive. But today's in CPU, multiply is kind of not that expensive. But generally it's much. It takes a lot more and effort to compute like a multiply than add or shift. So if you can, the compiler historically replaced this multiply instruction with, add and shift whenever possible. That's like a historic reason. So in this case, this part is computed using these two instructions. In the fifth instruction, we also again use like LEA. So in the LEA instruction, we actually have displacement, RDI, RDX. So actually this one effectively computes T5 because T3 is x plus 4, right? So if you unfold it, if you expand it, it will be x plus 4 plus T4, right? So we have just computed T4 here. So RDX is here, and 4 is here because this 4 is actually here, and RDI actually holds argument x. So this instruction actually computes sum of x and value of 4 and value of x, like value of T4. Okay, you add them up, and then that value will be stored in register RCX. In the last instruction, we multiply this RCX value by the value of RAX, which is like a T2, right? T2 is currently holding RAX, being held in RAX register. So we multiply these two values and store the result back to the RAX register. Okay? In our like a function call, like a calling convention, the return value must be placed in the RAX register. That's the convention. So before you actually return from the function, you place this return value in the RAX register and you return. Then the caller function will read this like a return value from RAX register. So that's basically how they communicate. Like caller and callee functions are communicate value with each other. So that's basically how this C code is compiled in the x86 assembly, x86-64 assembly, to be precise. Okay, so this one, this is it. This one actually includes the first part of the machine programming. So we already briefly covered Intel processor, architectures, history, and comparison between Intel and AMD, and so on. We also covered how these programs, the flow of translating these programs into machine code, starting from like a C, like a high-level language, and compiler kicks in to compile that into assembly code, and assembler translates this assembly code into machine code, bunch of ones and zeros, and the linker finally actually linking, they actually weave these multiple modules together to make the final exe, like executable file. And then now you can run it on native hardware. And we also covered assembly basics, register and move instructions, different different addressing mode, how you read, how you take the operands, like the value from, either from memory or constant or registers, and there are various like addressing mode. Also, we arithmetic and logical operations, like adds, sub, multiply, XOR, or, and so on, right? All right. That's it. Any questions? All right. Let's move on to second part of machine language. So in this lecture, we're going to mostly cover the controls. So control is, flow of your program, right? By default, your flow sequentially, right? You move on to next instruction. But sometimes you actually have branch. When you actually have if then else, then actually, depending on the condition, you actually go to here or go to then or else, depending on the condition, right? That's the example of a control divergence. Control may diverge depending on the condition. Another example is a loop, right? If you let's say you have a loop. So at the end of the loop, you evaluate the condition, and it satisfies the condition, then you go back to the head of the loop, right? Otherwise, you exit the loop. That's kind of another control divergence. That's program control. So the flow of your program. That's called control. And here, in this part of the lecture, which is covered in textbook chapter 3.6, we're going to go over various control mechanisms, like a loop, if then else, and so on, and how these kind of program patterns are translated into assembly language. So again, what I'm doing here is basically I show you very common patterns in your C program, like how those there are very common patterns, right, in your program, and how those patterns are translated into like assembly or machine code. Okay, to make good human compiler again. So in this case, in this lecture, we're going to see control like a conditional code and conditional branches like if then else statement and loops and switch statements. All these things, how these things are actually implemented in x86 assembly or machine code. So let's review. So if you remember, we actually have x86 ISA defines 16 integer registers, RAX, RBX, like a register R15. So there are 16 64-bit. Also, we actually have RIP. This one is called like instruction pointer, or in some literature, it's also called program counter. That's the same thing. So program counter instruction pointers are used interchangeably. So Intel folks call it instruction pointer or IP, but ARM people call PC program counter. They are the same thing. Basically, it points to the next instruction to execute in the memory. Okay. So here are like registers used for like temporary data. SP is used for special purpose. This is called like a stack pointer. SP stands for stack pointer, and stack pointer plays an important role when you actually call the function. Whenever there's a function call, you actually have to grow your stack, which will be covered in like next lectures. Don't worry too much about it. But the point is, this stack pointer is used for some designated like a special purpose. And location of the current code control point, RIP, like pointing to the location of the next instruction to execute. And also, there are some special flags called conditional code. So conditional code is basically, carry bit, overflow bit, 0 bit, and so on. They actually calculated implicitly by instructions. Okay, so if you, for example, you execute like an add instruction, as a result of a computation, these conditional fields are set implicitly, even though you don't really explicitly set it. You know, as a result of computation, it will be set automatically. So this one is called conditional code. You can actually make use of this conditional code to implement various like control instructions, such as if then else, you know, loop and while loop, for loop, and so on. So let's take a look at these control codes in more details. You know, there are four. You know, actually there are more than this, but initially, let's say we only have like 4, you know, single-bit registers or flags. You know, it's just nothing but a flip-flop. I mean, just you know, we have a 4 like a bits, like a 4 flip-flops, and you know those four flags are carry flag, sign flag, zero flag, and overflow flag. Okay, so how you know these flags are set? They actually set implicitly as a side effect of executing an instruction. So let's think about you execute this add instruction, add q. Then what you do is you compute the sum of these two, right? Then, of course, you compute the sum of these two and store to the register, destination register, right? That's what you do. But also, the CPU also, you know, set these flags as a side effect of this implicitly, okay? And these 4 flags are set. For example, this carry flag is set when the carry comes out as a result of this addition. Let's say you have 2 numbers, and then now you actually have the overflow from the MSB. Then now you actually have carry coming out of the right? And if it comes out as a result of computation, then the CF, the carry flag, is set to 1. Okay? The Z flag, like a 0 flag, if the result of this add is a 0. Okay? That's set implicitly, automatically set by the CPU. And a sign flag is set whenever the value, the MSB is 1. Is 1 negative value, right? If the result of computation is like a negative value, which means the MSB, the most significant bit, is 1, right? If the MSB is 1, then this S flag is also set to 1, sign flag. If it's 1, then it means like a negative number. Finally, the overflow is set if you actually have an overflow in 2's complement, like a signed integer computation. Okay? So how you detect whether this overflow happens or not? So there are only 2 cases of overflow, right? You add 2 positive number, and it goes beyond Tmax, then it's overflow. And also, the second case is you actually have 2 negative numbers, and if the number goes below Tmin, then you actually have overflow too, right? There are only 2 cases. So the way you detect the overflow condition is that both operand, source operand A and B, are positive value, but the resulting, the final outcome is negative value, then you know that, oh, there's, because if there were no, it should have been a positive one, but now you actually have a negative value, so you know that, oh, there was an overflow in this case. Likewise, if you had 2 like original, like a source operands of negative values, and the result is actually either like a 0 or a positive value, then you know that, oh, there was an overflow. Okay? So if any of these 2 conditions is satisfied, then this overflow field is set to 1. Okay? Note that you know, it's not set by the like this like a low defective address instruction. That's kind of, yeah. So it's not set by this instruction, but it's set by like any other like arithmetic operation, such as multiply, sub, you know, all these things. The second instruction of this setting this conditional code is CMP. CMP is basically, you know, compare. Okay, compare instruction. So compare instruction actually performs subtraction, like it takes like a basically calculation between the 2, but without writing a result to the register. It only just compare the value and set the flags, but do not really update any of the registers. That's like a CMP instruction. So if you execute CMP BA, then it's like computing like A minus B without setting the destination register. Only you just set the condition value, like condition flags, but the result is not really written to the destination. Okay. Likewise, it's very similar behavior. The carry flag is set if the carry came out of the MSB of the operands. Also, zero flag is set if the final result of computing this A minus B is 0. So A minus B equals 0 means that A equals B, right? So in this case, if you want to compare whether these two values actually have the same value or not, what you can do is you execute CMP instruction and then check this zero flag. So if zero flag is 1, that means you know that these two values are the same, right? And the sign flag is if the computed value A minus B actually has 0, actually negative value, then you actually set this sign flag to and it's like before. So if you actually have two operands, if the overflow happens as a result of computation, then now you set this overflow bit to 1. Because now we compute this A minus B, the overflow condition will be if A is positive and B is negative, then it can be actually go above this T max. Or if A is negative and B is positive, then actually it can go below T min, right? There are two cases, right? Likewise, like before. 네. 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 그 구분을 하는 건 아니고요. 사실은 이게 사인드랑 언사인드를 구분해가지고 따로따로 뭔가 다른 방식으로 처리하는 건 아니고요. 이게 사인드 오퍼레이션이든 언사인드 오퍼레이션 일단 그냥 비스팀을 보고 이건 기계적으로 결정이 되는 거고 실제로 이 플래그가 사용되는 거는 예를 들어서 오버플로우 플래그는 언사인드에서는 사용 안 되겠죠. 그러니까 똑같은 그냥 하드웨어는 어차피 똑같이 그냥 기계적으로 그냥 값을 보고 이런 조건을 만족하면은 이제 그 오버플로우 플래그를 세팅을 하는데 실제로 사용되는 거는 요 두 경우는 사인드 연산을 할 때만 사용이 될 거고 요 경우는 언사인드 계산을 할 때만 사용이 된다는 거죠. 그러니까 이 밸류를 세팅하는 것 자체는 사인드인지 언사인드든 언사인드든 상관없이 똑같은 그냥 기계적으로 하드웨어 로직 세팅을 하는데 실제로 이 값을 참조를 하는 경우는 예를 들어서 이 두 개의 플래그는 사인드 연산을 할 때만 참조를 하게 될 거고 요 플래그는 언사인드 연산을 할 때만 참조를 하게 된다는 거죠. 구별 안 하죠. 구별 안 하고 그냥 하드웨어적으로 처리를 하고 이 값도 사인드, 언사인드 구분하지 않고 그냥 하드웨어가 그냥 기계적으로 세팅을 하는데 실제로 이 값을 쓰는 경우는 이 플래그를 쓰는 경우는 사인드 연산을 할 때만 쓰이고 이 플래그를 쓰는 경우는 언사인드 연산을 할 때만 쓰인다는 거죠. 잘 약간 아리까리한 것 같은데. 그렇게 볼 수도 있겠죠. 그렇게 볼 수 있나? 그러니까 쉽게 말하면은 뭐 쉽게 말하는 건지 모르겠지만 이 덧셈의 결과나 예를 들면 덧셈이나 아니면 CMP를 계산할 때 그 결과나 이 레지스터의 값은 일단 첫 번째로 CPU는 내가 지금 들고 있는 그 레지스터의 값이 사인드인지 언사인드인지 전혀 감이 하나도 없어요. 그냥 얘는 단순하게 비스트림으로만 이거를 그냥 처리할 뿐이고 그다음에 어떤 규칙에 의해서 그러니까 덧셈의 규칙에 의해서 실제로 리절트를 계산하고 그다음에 이 플래그 bit들도 그 기계적인 그냥 그 로직에 의해서 그걸 세팅을 해요. 근데 나중에 이제 휴먼 프로그래머나 이제 컴파일러 입장에서는 이게 실제로는 언사인드 인테저다. 사인드 인테저라는 거를 그걸 해석하는 입장에서 알 거 아니에요. 그럼 예를 들어서 내가 두 개의 언사인드 인테저를 만약에 덧셈을 했는데 하고 싶다. 그러면은 여기에서 OF라는 오버플로우 플래그를 봐야 되겠죠. 근데 만약에 내가 두 개의 언사인드 인테저를 덧셈을 했는데 오버플로우가 났는지 안 났는지를 보고 싶으면 봐야 되겠죠. 근데 그거는 컴파일러나 이제 그걸 쓰는 사람은 알죠. 내가 지금 디텍터에서 캐리 플래그를 봐야 되는지 오버플로우 플래그를 해야 되는지는 그 컴파일러나 아니면 어셈블리 코드를 작성하는 사람은 알지만 기계는 그냥 단순하게 이거를 세팅하는 거는 기계적으로 아무런 사인드든 언사인드든 상관없이 똑같이 그냥 계산해서 내오는 거죠. 네, 뭐 설명이 됐는지 모르겠지만 하여튼 네. 하드웨어는 되게 무식해요. 하드웨어는 되게 무식하게 그냥 단순하게 그냥 주어진 일만 주어진 법칙 룰에 의해서 그냥 하는 거고 실제로 쓰는 거는 이제 사람이나 컴파일러가 이제 알고 그걸 어떻게 해석해서 적당한 이제 그 하는 이제 플래그 체킹하는 이런 것들을 넣어주겠죠. 명령어들을. 네. 왜냐하면 저 페어가 A 빼기 B를 하는데 왜냐하면 보통 이제 어떤 경우에 많이 쓰냐면은 두 개의 오퍼랜드의 값이 같냐 다르냐 이런 거 체크할 때 많이 쓰거든요. 티피컬한 사용 예가 A하고 B가 똑같은 값을 갖고 있냐 아니냐, 이퀄이냐 안 이퀄이냐. 보통 뭐 이런 거, if A 이런 거, 그죠? 이런 거를 만약에 계산하려고 그러면 두 개 사실은 비교하는 방법이 이제 이게 사실은 두 개를 빼가지고 0인지 아닌지를 보면 되잖아요. 그러면 더 쉬운 컴페어하는 방법이기 때문에 그냥 값의 이퀄리티를 컴페어한다고 생각하시면 될 것 같아요. 근데 사실은 B를 계산하면 이것도 계산할 수 있고 만약 A 빼기 B를 계산하면은 이런 경우가 있고 이런 경우가 있고 이런 경우가 있겠죠. 그죠? 그 값이 이제 포지티브 값인지 네거티브 값인지 이거에 따라 가지고 이게 0과 같은 경우도 있고 0보다 큰 경우도 있고 0보다 작은 경우도 있겠죠. 근데 이걸 보면은 두 개 사이의 그 대소 관계를 비교할 수 있잖아요. 어떤 애가 더 큰 값인지. 그죠? 그래서 실제로 컴페어라고 부르는 거고요. 그냥 뺄셈 하는 거예요. 근데 뺄셈을 하지만 그 뺄셈의 결과 자체는 레지스터에다 업데이트하진 않는 거죠. Okay. The next is called test. Test is like similar to CM, but what it does is it computes the end of the two operands, A and B. Okay, so it computes the bitwise. This is like bitwise end, right? Use like bitwise end, and you compute this thing without actually updating the destination field. So conditional code is set based on the result of this computation, A and B. Usually zero flag and sign flags are useful for this like instruction. So you can check whether the value is 0 by looking at the zero flag, and you can also check the sign of the result by looking at the sign flag. Okay. Also, there are some like instruction for reading like conditional code. So you can actually copy the value of this conditional code into purpose register. So let's say set E means like if the zero flag is 1, then the register value is set to something like, let's say set E something like a register like so let's say set E something like AL. So this one is kind of example. This AL is this LSB of the register, because it actually takes the a byte as a destination. Then what it does is it sets the value of this register, like the LSB of the register. So if let's say you have a set E, that means if currently the zero flag is set to 1, then this AL register to 1, otherwise it will be set to 0. And if you actually execute set any not equal, and the output will be this register will be set to 1 if zero flag is 0. Likewise, set S if you execute set S instead of like a set E, then this AL register will be set to 1 if the sign flag is 1. And set NS is, if this value will be set to 1 if the sign flag is 0. So all of these things basically, corresponds to some like either simply reading this like a flag, or some like combination of the flag. So you can actually use set G for a greater than or equal, set GE, set L, set LE. So all these things are basically used for different conditions to detect like detect some conditions after you do some computation. And it only sets the low order byte, the LSB, of the destination to either 1 or 0 based on the combination of condition code. If this condition is satisfied, then the value is set to 1, otherwise it's set to 0. And it does not really change the value of the remaining like upper 7 bytes. So as I have shown you, the set X instruction only affects this part of the register, but the remaining like 7 bits are unchanged. Okay. So here's an example usage of conditional code set X instruction. So let's think about this example. This is a simple function that actually takes 2 integer as input, and it returns 1, like a true, like a 1 if X is greater than Y. Otherwise, it returns 0. That's what this function do. And here the assumption is, we actually takes these 2 arguments through register RDI and RSI. These 2 registers hold the value of X and Y initially, and we return the value through RAX register. That's the convention. So here, how this function can be implemented. So let's do it. So first, we compare the value of the 2. So RSI, RDI. So in this case, it computes the difference between, it's like a computing RDI minus RSI, right? Computing the difference between the 2. And set GL. So that means if one is actually greater than the second one, if greater than the second one, then this AL register will be set to 1. Otherwise, it will be set to 0. And this move ZBL this one looks complex, but this one actually stands for move 0 extended byte to double word. So that's the reason why it's like a move ZBL. I don't know, something like this. So move 0 extended byte to double word. So basically what it does is it takes like a single byte as a source, and then it 0 extend. So 0 extend means that it pads all this upper like a 7-bit with zeros and copy the value to the destination. Okay. So in this case, it's double word. So this one is like 30. So it will be the EAX register will be holding either 0 or 1 depending on the value of AL, and it returns. Okay. So that's basically how we use this set instruction. So it basically copy the condition, detect the condition using this flags, and then it copies the value to the general purpose register, in this case, or RAX. Because if you execute this move Z BL, then it also sets the upper 32-bit to 0. What happens is, this LSB will be set to either 1 or 0, depending on the result of computation. And if you execute move like a ZBL, move ZBL instruction, then all of this like a value will be set to 0 before you return. And then you return, then actually this like a result will be held in RAX register. Okay, so I think time is up. So I think I'm going to stop here, and I'm going to continue this conditional branches after Chuseok. So I hope you guys great vacation for Chuseok, and hope to see you guys in like 2 weeks. please be sure to submit your homework before you're going home. Okay? All right. Have a good holiday.